Problem number 16. A massless spring with a spring constant K is vertically mounted so that the bottom end is firmly attached to the ground and the top end free. A ball with mass M falls vertically down on the top end of the spring, becoming attached, so that the ball oscillates vertically on the spring. What equation describes the acceleration of the ball when it is at height y above the original position of the top end of the spring? Let down be negative and neglect air resistance. G is the magnitude of the acceleration of free fall. So first let's draw the picture for this process. Initially a spring is in neutral position, and after mass is attached to the platform, it starts to oscillate in the position y above the neutral. We can figure which forces acting on this mass. So first force is from spring. It's equal to negative ky, because y is positive, and it's a regular formula for force with a Hookean spring. And other force is mg, which is going to negative 2. So we can write this equation. So that's the equation for motion for this ball. And now we can find what is the acceleration. This is the final equation for acceleration. So we can see that it's exactly E, correct answer. Problem 17. A mass M is resting at equilibrium, suspended from a vertical spring of natural length L and the spring constant K, inside a box as shown. The box begins accelerating upward with the acceleration A. How much closer does the equilibrium position of the mass move to the bottom of the box? So first of all, we can write equation for how to find what is the displacement of mass from initial equilibrium to equilibrium with the mass attached to the spring. mg equal negative kx1. If we start to move this box upward with acceleration A, its best way to do is to move to the new frame of reference, which is going with acceleration A upward. In this frame we have additional frictional force, like additional force of gravity acting on all bodies. So it means that we can replace gravity acceleration G with the gravity acceleration G plus A. In that case, a new equation for the equilibrium position will be this one. So now let's subtract from this equation which describe what is the displacement of our new equilibrium position. That's x2 minus x1. x2 minus x1 equal negative ma over k. So, and the question was what is the new position down to the bottom. So it means that answer is ma over k, which is E. Problem number 18. A uniform circular ring of radius big R is fixed in a place. A particle is placed on the axis of the ring at a distance much greater than R and allow it to fall toward the ring under the influence of the ring's gravity. The particle achieves a maximum speed v. The ring is replaced with one of the same linear mass density but radius 2r, and the experiment is repeated. what is the new maximum speed of the particle. So first of all, if we are very far from ring, we can make potential energy equal 0 in the infinity. And now let's calculate what is the potential energy in the center of the ring when particle achieved it. That's obviously be this expression: potential energy equal negative g, mass of the ring multiplied by mass of the body and divided by radius, because all mass of the ring has a distance r from the center of this ring. It means that this particle will get kinetic energy equal to difference of potential energy, K equal positive expression for potential energy. Now let's see what happens if we have double ring with the same linear density and repeat this experiment. If we double linear density, it means that total mass of the ring will double, but the distance from the center of the ring will double too. So it means that for expression for potential energy will be like this: we double mass, we double radius, they will cancel each other, and potential energy will be the same. It means that particle will get the same kinetic energy, which means that speed, maximum speed will be the same. So correct answer is C.